Hi everyone, myself Dilip Krishna. Today I am here to explain about the topic of 2D pipeline, 3D pipeline, RGB and CMY color model. So let us discuss about 2D pipeline. In computer graphics, a 2D pipeline refers to the sequence of operations and transformations that are performed on 2D geometric data to generate a final image or output. This pipeline typically consists of several stages, each responsible for specific tasks. Here is a general overview of the stages in a 2D graphics pipeline. Geometry definition. The pipeline starts with the definition of geometric primitives in 2D space. This could include points, lines, curves, and polygons. These primitives are usually represented by their coordinates or equations. Vertex processing. In this stage, the attributes of the vertices such as position, color, and texture coordinates can be modified or interpolated. This can involve transformations such as scaling, rotation, translation, or sharing to position the primitives correctly in the 2D space. Clipping and culling. After vertex processing, the primitives are checked against the clipping region to determine if they lie within the visible portion of the screen. Primitives that are outside the clipping region are either discarded or clipped to fit within the visible area. Additionally, backface culling can be performed to eliminate primitives that are facing away from the viewer. Primitive assembly. This stage collects the processor vertices into geometric primitives such as lines or triangles. For example, a set of 3 vertices can form a triangle primitive. Rasterization. The rasterization stage takes the geometric primitives and converts them into a set of fragments or pixels. This process involves determining which pixels within the primitive's boundary should be considered as part of the primitive. Fragment processing. Each fragment generated during rasterization goes through fragment processing. This stage applies operations like texture, mapping, shading, and lighting calculations to determine the final color properties of each fragment. The last part is pixel operations. Finally, the processor fragments are mapped to the corresponding pixels on the screen or output device. Operations like alpha blending, depth ranging, and stencil testing can be performed to determine the final color and depth value for each pixel. These stages represent a simplified overview of the 2D graphics pipeline depending on the specific rendering system and requirements. Additional stages or variations of these stages may be included. However, this general pipeline provides a framework for understanding the process flowing 2D computer graphics. So let us discuss about the second topic, 3D pipeline. The 3D pipeline in computer graphics refers to the series of stages and transformations involved in rendering a 3D scene into a 2D image. It encompasses various processes that converts 3D geometry and associated attributes into a final rendered output. Here is an overview of the stages in a typical 3D graphics pipeline. First one is geometry definition. The pipeline starts with the definition of 3D geometric data such as vertices, edges, polygons, and other primitives that make up the 3D scene. The geometry is typically represented by its coordinates and connectivity information. Second one is vertex processing. In this stage, individual vertices undergo transformations including translation, rotation, scaling, and sharing to position them correctly in the 3D scene. Additional vertex attributes such as colors, texture coordinates, or normals can also be modified or interpolated. The third point is clipping and culling. After vertex processing, the primitives are checked against the viewing frustum to determine if they lie within the visible portion of the scene. Primitives that are outside the frustum are either discarded or clipped to fit within the visible region. Backface culling can be performed to eliminate primitives that are facing away from the viewer. Fourth point is primitive assembly. This stage collects the processor vertices into higher level geometric primitives such as triangles, quadrilaterals, or more complex polygons. Based on the connectivity information, for example, a set of 3 vertices can be form a triangle primitive. The topic is geometry processing. Once the primitives are assembled, additional operations can be applied to them, such as tessellations, displacement mapping, or procedural modeling. These operations can add detail or modify the geometry to enhance realism or achieve specific artistic effects. The sixth topic is rasterization. The rasterization stage converts the geometric primitives into fragments of pixels. It determines which pixels within the primitive's boundary should be considered part of the primitive. This involves interpolating attributes like color and texture coordinates across the primitive surfaces. 7. Fragment processing. Each fragment generated during rasterization undergoes fragment processing. This stage applies operations like texture mapping, shading, lighting, calculations, and other material properties to determine the final color and properties of each fragment. Depth testing and blending. The fragments are then processed for depth testing, which determines whether a fragment should be drawn based on its depth value relative to other fragments. Blending operations can be performed to mix fragment colors with existing colors in the frame buffer, allowing for transparency and other visual effects. Output method. Finally, the processor fragments are mapped to the corresponding pixels on the screen or output device. The output method state combines the fragments based on their depth values and resolves any conflicts or overlaps, resulting in the final color for each pixel. The 3D graphics pipeline described above provides a high-level overview of the stages involved in rendering a 3D scene into a 2D image. Depending on the specific graphics system and requirements, there may be additional stages or variations of these stages involved in the pipeline. Let us discuss about the RGB and CMY color model. RGB color model. The RGB color model is an additive color model, meaning that colors are created by adding various intentions of red, green, and blue light. In this model, the primary colors are red, green, and blue, and they are combined in different portions to create a wide range of colors. The RGB color model is widely used in computer graphics because it closely corresponds to how colors are displayed on electric displays such as monitors and screens. In the RGB model, each color component red, green, and blue is typically represented by an 8-bit value ranging from 0 to 255. By varying the intensity of each component, we can create over 16 million possible colors. For example, pure red is represented as 255, 0, 0, pure green as 0, 255, 0, and pure blue as 0, 0, 255. Mixing these primary colors in different intensities allows you to achieve any desired color. CMY color model. The CMY color model is a subtractive color model primarily used in printing and mixing pigments. It is based on the concepts that when pigments are mixed, they subtract or absorb certain wavelengths of light, resulting in the perception of different colors. In this model, the primary colors are cyan, magenta, and yellow, which are subtracted from white light to produce colors. In the CMY model, each color component cyan, magenta, and yellow is also typically represented by an 8-bit value ranging from 0 to 255. A value of 0 represents the maximum amount of that color component, while 255 represents the absence of that color component. To achieve a desired color, the ink levels of cyan, magenta, and yellow are adjusted and layered on a white substrate. For example, pure cyan is represented as 0, 255, 255, pure magenta as 255, 0, 255, and pure yellow as 255, 255, 0. Combining these subtractive primary colors in different intensities allows you to produce a wide range of colors. Both the RGB and CMY color models have their specific applications in computer graphics and image processing, with RGB being dominant for electric displays and CMY used in printing and color mixing with pigments. Thank you.